Hello my friends, in this video we're going to talk about induced currents, and main objectives are to understand how they happen, which happens to be change in magnetic fields, understand how motional EMF happens. EMF is electromotive force. As we learned before, batteries has internal electromotive force that causes the charges to go push through a system and generate currents, and calculate it. So this idea of induced current based on series of experiments by Michael Faraday. So he's the father of understanding of the induced current. One of his experiments was to wrap around a wire in an iron ring, as you see in this figure here, and drop another wire on the other side, and notice they are not touching to each other than through this ring, and close the switch and see what happens. And what he saw, that he was wondering if there was any effect of the current passing through here on the second wire. And what he saw was that over here he was seeing current, so current meter, ammeter was changing just as he was closing the switch. After a while it stops, and as he was opening the switch, same thing happened. Current passed through, he read the current, it was in the other direction, but he read the current only when he was opening the switch. After a while it stops. We already learned that if we have loops here, current passing in this fashion here, we'll have a magnetic field, right? And that magnetic field will behave like a bar magnet. These are loops. We can also treat them as solenoids. So as we close the current, the switch, and current starts passing through, the magnetic field on the left will increase, reach to a value until the system sets up, and then it will have a constant value. As we open the switch again, this magnetic field will drop to zero, and it will take some time to drop to zero. It seems like as the magnetic field is changing, he was seeing a current here. So that's what he suspected. If B changes, there is a current. On the right circuit. He tried some other experiments. Similarly here, now they're not connected at all through an iron bar or so, and he saw the same thing. He closed the switch, saw a current here, opened the switch, he saw a current here, and they were in opposite direction. Again, only when magnetic field is changed. He tried several other experiments, like this one here. Putting a bar magnet inside a loop and taking it out generates current. If I put it inside and leave it there, don't move it, no current. Similar idea here, I'm putting a loop inside a magnetic field. I have a very strong magnetic field in between these two poles here. Outside we have a weaker one, so magnetic field increases as I put the loop in, and decreases as I put the loop out. So here B increases going in, here B decreases. In each case we have a current generated in the system. It boils down all the same idea. If the magnetic field is changing, it induces a current in a system. That's the bottom line here. Another idea he worked on was to move a conductor through a magnetic field, and he also saw that changes happens, and he also saw that the charges are separated. We already know that from a previous unit that if we move charge through a magnetic field will apply a force to it, right? Depending on what is the angle between the magnetic field and the velocity. Over here, so we know conductors has plus and minus charges, so if I move a conductor through a magnetic field, it is as if I am moving charges through a magnetic field. So magnetic field will apply force to charges. Applying my right hand rule 3, I'm going to put my arm and hand down along the velocity, right? Then I'll curl my fingers towards the magnetic field, which is out of the board. Again, I'm not doing a great job in drawing this, but I'm hoping everybody is understanding. And this is the magnetic field out of the board. And as I do that and open my thumb, it will be to the left. So, oops, I'll use blue here. At least they're all the same color. It's a bad picture. Alright, and that will be the force on positive charges, right? That means positive charges will be pushed in this direction. And force on negative charges are always opposite, so they will be pushed in that direction. And after a while, we'll have this. And guess what? We separate the charges. If we have a separated charges, a group of separated charges, plus and minus, we will have a potential difference. To keep them separated, we have to keep moving the bar. We stop, they will go back to their original position because there's a potential difference. Remember, positive is high potential, negative is low potential, and positives will want to move to the right, negatives to the left. That's how they move. And they will rearrange, go back to their original position. Also remember that there is an electric field from plus to minus. Why the charges move? Because we have high potential and low potential. Or electric field pushes the positive charges along the same direction of itself and negative charges on the opposite direction. So if I stop the motion, these charges will go back to their original position. But as long as I am moving the bar, they will stay. Magnetic field will push them in those positions. And remember, if electric is equal to Q times E, if I know the charge in electric field, I can calculate that. So this is also an induced electromotive force or potential difference, and we can harness that. Here are some examples of induced currents and induced potential difference. Hammerheads moves through the Earth's magnetic field. It's likely that they detect the magnetic field using their keen electric sense, detecting the Earth's magnetic field by sensing the motional EMFs as they move through the water. So, assume they're moving in this direction. This is the velocity in the head, and magnetic field is down, the Earth's magnetic field. That is not exactly correct. There will be angles, of course, not perfectly 90-degree angles, but let's assume it's so. Using my right-hand rule, I can find which direction plus and minus charges would be moving in this hammerhead's head. And it happens in the whole body too, but I'm going to show it in the head. So right-hand rule 3, I put my hand along the velocity, right? And then roll my fingers towards the magnetic field down. And this is not gonna be at all a perfect picture, but the force will be if I open my thumb like that, the force will be this guy over here. So force will be out of the page in this case. If this is the velocity is to the left, input the magnetic field is to the down. Out of the screen. So we'll have plus charges coming here, around here, and minus charges going there. There will be a potential difference in between these 2 points of hammerheads. He will have high potential here and low potential there. And he will have an electric field. He feels that changes, and that gives him an idea of where he is. In 1996, astronauts on Space Shuttle deployed a satellite at the end of a 20-kilometer conducting tether, and they developed a potential difference here and there. It was simply a conductor moving through a magnetic field. Again, we can make up directions and find where positive and negative charges would go. This would be the velocity. Let's say it's going in this direction, and let's assume that the magnetic field is towards us. Let me use the red, blue doesn't look here. Oops. Alright. And magnetic field is towards us. Right hand rule again. Right hand rule 3. Roll your fingers along the speed. Put your arm and hand along the speed. Roll towards magnetic field. Open your thumb. In this situation, your thumb will be up. Don't look at my picture, but do this with me here. Force should be up. Again, magnetic field is towards us. Out of the screen, I try to draw them, and the velocity is to the left. Both are tilted a little bit, and the force is upward, tilted as well. So the force on the positive charges would be up in this picture. Remember, we always find the force for the positive charges as we do right hand rule 3, and that for the negative charges in the opposite direction. So here is what will happen, and we will develop a potential difference. They happen to develop about 3,500 volts potential difference. It's amazing. How can we calculate stuff about that? We can harness this, we can use this, we can use them as batteries after we separate. And we can guess how much power we can get from them. Using the idea that if I'm moving my bar with a constant speed, that means that the force I applied should be equal to the force of the magnetic field. But first let's look at this idea here. How long, if I keep moving my bar inside the magnetic field, how long will it continue separating charges, right? And will it stop or keep separating charges? What will happen is that as the charges are separated, so here again, right hand rule 3, put my fingers along the speed velocity, roll them towards magnetic field. This is kind of into the board. We will see that the force is upward here. So magnetic force is upward. It's called FP. And the positive charges will keep going here, and negative charges will come down there, but we know that there will be an electric field generated from plus to minus as the charges are separated, which is why we also have a potential difference. And we also know that electric field will apply forces. Let's look at the positive charges only. Electric force applied to positive charges is in the same direction as the electric field. Now, above we saw magnetic force is in the opposite direction. As more and more charges are separated, electric force will increase because it's equal to Q times E. And separation will increase E. And what will happen at some point, electric force will be equal to magnetic force. What can we do is to put down the equations. Remember, electric force QE, magnetic force QVB. Here alpha is 90 degrees again, so we're dropping sine alpha. Always keep in mind magnetic force is actually QVB sine alpha. But if alpha is 90 degrees, like in this picture, sine alpha is 1, so it is dropped. We can calculate electric field generated using QE is equal to QVB. At the point where we reach equilibrium, the electric force is equal to magnetic force, and charges are not going to be separated anymore because that electric force will stop the separation. And here is our electric field. We will calculate from there. Then knowing the equation between the potential difference in electric field, potential difference equal to E times D, electric field times the distance. So if I'm looking at between two distances and thinking about what is the potential difference in between, let's look at the edge here to make it more correct. If I know the electric field and this distance, I can calculate it easily, E times D. And in the case of the wire, we take the distance as the length of the wire. That's why we have L here. But that's simply, this equation is simply the same as that. So once I can calculate the electric field, I can calculate the potential difference. And if I like, I can enter this equation here to get the second equation. VLB is equal to potential difference generated. And that's actually what is called motional EMF. So we're going to call it epsilon. Here is the summary. We generate motional EMF. Our bar, our conducting wire or bar looks like a battery, behaves like a battery, and we can find its potential difference or electromotive force, to be more correct, as the velocity times the length of the wire times the magnetic field, background magnetic field. That's one thing. And this question here is applying that. We have an aircraft moving with a wingspan of 60 meters. Speed is 260 meters per second, and it's moving through a magnetic field, the Earth's magnetic field, that is equal to this much. What is the potential difference between the tips of the wings? Now, as the airplane moves, let me try to picture that as well. Assume these are the wings and they're moving in this direction. And magnetic field is down. If I do V cross P, fingers, hand along velocity, then we curve them down, right? My thumb will be in this direction, so this will be F. This will be force applied to positive charges. Positive charges will come here, negative charges will go there. Again, do this with me to see that is the case. So they will generate a potential difference delta V. How I can calculate that as V, velocity, length of the wings times the background magnetic field. There are a lot of readings here, but be careful and understand what's happening. You will see it's just a plug and chug question. I'm moving a metal bar parallel to magnetic field here. Is there an induced current? Is there an induced potential difference, or how the charges will move here? Parallel motion, remember, no charges, no moving. Everybody stays as they are. The induced charges on the bar are none. No induced charges. So that's the answer. In this one, we are given the motion, direction of the motion, and we actually connected the bar that we're moving through a magnetic field to a circuit, and we generate the current. We can do it. That's how we harness the emotional EMF. If we put a light bulb here, for example, we can light it up depending on how much current we are generating, right? The question tells us if the current generated in the system is in this direction and the velocity is to the right, what is the direction of magnetic field? And we will use right-hand rule. Two information we use here. First, the direction of conventional current is always from plus to minus. That means this side should be plus, upside, and the downside should be minus for this bar. That means the magnetic force applied to positive charges I'm going to call F magnetic positive. Just to keep in mind that right hand rule 3 gives us the direction of force applied to positive charges is upward. So what should be the direction of magnetic field? That when I put my fingers along speed, my thumb will end up being along force, which is upward here. When I curl my fingers towards the magnetic field, so you're kind of walking backward here. Put your fingers, 4 fingers, along the speed, velocity, and then turn your thumb towards the force that you know. After you do that, just curl your fingers. The direction they are showing you is the direction of magnetic field. That would be into the board here. Again, not a great picture here, but B is into the board. Generators uses the idea of change in magnetic field. We'll get into this further in the future. To generate currents. Over here, what we do is we rotate this coil, and as we rotate it, what happens is that the magnetic field passing through the coil changes, and that generates a current. That is an induced current here. And that's how actually we generate power for our homes. We send it to our home, take care of it with several devices, so we'll have it more efficiently used, and we will have our power system. So the idea behind electric power plants is an alternating current is induced currents. Now if I, again, as we've talked before, if I move my conducting wire, make it into a battery, right, so generate a motional EMF, and I can connect it to a circuit, I can harness that current. It will be moving charges from this direction. As long as I keep moving my bar or wire inside the magnetic field, I will have this current. I can actually calculate that current. If I know the motional EMF, which is we can calculate using VLB, right? We talked about that. And if I know what is the resistance of, let's say I put a light bulb here and it has an internal resistance, I want to calculate how much current is passing through this light bulb. I can't. All I have to do is use my famous Ohm's law. What does it say? Current is equal to potential difference divided by R. And our potential difference here is motional EMF. Again, we can go ahead and use delta V for it, but our book uses epsilon, so we're gonna stick with epsilon. But it's the same as delta V, potential difference. And if I like, then I can enter the VLB over R. This equation here is from the book. I don't really like having an equation in this fashion, but book gives it, Master in Physics gives it, so I keep them here. But the idea is get the epsilon and use Ohm's law to get I, right? That's working through logic, not just putting things into equations. So yeah, as we pull the object, we can think more about idea of moving an object with a constant speed. If V is constant, total force is 0, so forces to the right are equal to forces to the left. Tells us that the pull force that I'm applying should be equal to magnetic force. And we learned that magnetic force on a current carrying wire, this guy will turn into a current carrying wire as I move it, as ILB. I can also use that to get the magnetic field. And guess what that gives me? What is my pull force? So if I'm asked to find the pull force, all I need to find is the magnetic force. If I like, again, I can input this current here and turn it into a more ugly looking equation. Again, I don't really like the general idea. I want you folks keep in mind here is that F pull is equal to F magnetic. Then using the fact that F magnetic is I current times the length of the wire times B, we can also find the pull force. How do we find current again? From Ohm's law. We can go even further, look about the power can be calculated force times the speed or velocity. Remember, power is still change in energy divided by time or work per unit time, right? Work is equal to change in energy. We can use these ideas to calculate power or even energy in the system and so on, or work done. If my F is equal to F pull, I can say F pull times V. Remember, F pull, if my object and my wire is moving with a constant speed, is equal to F magnetic. So these are all different ideas we can see around. Remembering that power dissipated can also be calculated using I squared R. We talked about powers in circuits, so we can also use this. Now the last equation here again is in the book, so I put it here, but it wasn't necessary. This is just inputting I is equal to V L B over R. Is it that? Yes. So if you input this guy over here, we can get this equation. Here's a question involving power. We have a bar, we're moving it, pull force, velocity, and length is L, in a magnetic field that is B. Alright? And the total resistance of the wire and the rail. So in the system there's a total resistance. I'm going to symbolize this as if I have a resistor here. So we have an R. And that resistance is equal to 0.2 ohms. And we're pulling the wire with a force of 1.0 Newton. And the power, this is F pull. Remember, this was F equals to F magnetic if our velocity is constant. And we won't be looking into situations where we're increasing the speed or so on. So we can safely say in this situation, F pull is always equal to F magnetic. And the power that is generated in the system is 4 watt. Remember, unit of power is watt. What is the speed of the wire when pulled with 1 Newton? Very simple matter here. Power is equal to force we apply, which is F pull, times the speed. And that will give us a speed of 4 meters per second. B, what is the strength of the magnetic field? I could go here and use this equation that I don't really like. Power dissipated is equal to V squared L squared B squared over R, and solve for B. Or I can say, if power dissipated is this, I can get my current. Then I can use my current to find B, which is the way I want to go here. So power is equal to I squared R. Then I squared, divide each side by R, will give me power divided by R. Take square root, this will give me the current. I is equal to square root of power over R. So get your current from here. Alright, and then you say F pull is equal to F magnetic, right? So, and F magnetic equation is I, L, B. So if I know the current, this I do from here. I know L, the length of the wire, 10 centimeters, which I forgot to add here. L is equal to 10 centimeters, 0.1 meters. I can get B. Divide each side by IL. Rearrange. I'm going to have B to be equal to force of magnetic force divided by current times L. Insert, insert. F pull is given as 1 Newton, so F magnetic is also 1 Newton. Insert, get B. B should be about 2.24 Tesla. Alright, that's it. I'll see you on the next lecture.